Hello, dear colleagues. I would like to present a joint paper by Dr. Sukhoruchkin from National Research Center Kurchatov Institute and Dr. Sakharov from Bauman Moscow State Technical University. The title of our work is Calculation of the Dose Coefficient for Radioactive Aerosol of an Arbitrary Disperse Composition. To begin with, let us define what is a dose coefficient. A dose coefficient for an aerosol called E50 is the value of the human's irradiation dose caused by radionuclide inhalation intake in the quantity of 1 activity unit, measured in sievert over becquerel. This is one of the key metrics for radiological safety and radiation medicine applications. A dose coefficient depends on the dispersed composition of an aerosol. If this coefficient is known, we can determine the exposure dose E using the formula E equals E50 times I. Here, I is the measured value of radionuclides intake by the organism, measured in becquerel. Dose coefficient depends on different physical and chemical properties of radionuclides, and in particular, on the aerosol dispersion. Today, the ICRP database is widely used to determine dose coefficients for different radionuclides, and those coefficients presented in this database are calculated in assumption that the distribution of radionuclide activity over the aerosol particle follows log-normal distribution presented on this slide. Here we have phi of dA is the distribution density of the aerosol's activity over particle's diameter. dA is the aerodynamic diameter of a particle. A is the aerosol's activity, and also we have a couple of distribution parameters, dA0, which is aerodynamic median activity diameter, and S, which is a standard geometric deviation. But here on this slide, we present an example of this ICRP database table for plutonium-239. And here we have 10 log-normal distributions, I running from 1 to 10. And each log-normal distribution corresponds to a dose coefficient with the proper set of parameters, which is a diameter and a standard geometric deviation. So why can't we just use this database when we need to determine those coefficients, and why do we need to propose a new method? The fact is that real measured values of the aerosol's activity over particles' diameters can have different conditions. And those conditions can be different from ones used for calculations. For example, they can have different distribution type, or can be the same distribution but with different parameter values, etc. And therefore, for the purpose of radiological protection, it is required to have a method suitable for estimating the coefficient E50 with an arbitrary dispersed composition of an aerosol. Let's briefly discuss the physical meaning of our method. It is based on the idea that a deviation from log-normal activity distribution can be a result of existence of two or more sources of aerosols on different dispersions. For example, representing mechanical, thermal, and hydraulic effects of on radioactivity, radioactively contaminated surface, which can happen in practice, obviously. We present the following method. It is based on the use of already known dose coefficients from the ICRP database, but at the same time, it uses the experimentally measured distributions, and we try to approximate them with the sum of several log-normal distribution functions Fi that can be seen in the ICRP database. So the resulting function is presented on this slide, Formula 1, and it is the sum of Fi and corresponding weights Qi. Also, we have several restrictions imposed on these weights. For example, the value of each weight should be within the interval from 0 to 1, and the sum of all weights should be equal to 1. Fi, as I have just said, is the cumulative function of log-normal distribution, and we can define this function as formula 2 as an integral with the upper limit dA. So functions Fi have the following known parameters: diameter and standard deviation, which match the values from the table on slide 4. And these distributions are used in the ICRP database, and for them we have known coefficients E50. If we plot these functions in a log-normal probabilistic scale, they will be seen as straight lines. And as a part of this study, we have developed an algorithm to plot these graphs in a log-normal probabilistic scale in Maple software, which was not presented in a standard set of packages. So now we should define that the value of Fi equals the fraction of aerosol's activity delta associated with particles. And we have a diameter value in the range between 0 and dA. If we approximate any experimental distribution, in other words, we have a set of functions, Fi, and we have their weights somehow calculated, then we can calculate a dose coefficient E50 approximated that corresponds to the required approximating function F1. And this E50 approximated can be determined as a sum of those values where we have E50I, which are the dose coefficients from the table, and corresponding weights. So now the task that we have is to calculate weights. So we can determine those weights using the least square method. And in other words, we transform the problem into the optimization problem with the following objective function y of q. Here, p is the measured value of the cumulative distribution function obtained during the experiments, and m is the number of points used for measurements. Of course, the more points we have, the better results will be. Thus, the required weights that minimize the value of function y can be determined from a set of equations presented in Formula 5. On this slide, we have described the procedure for calculating weights Qi. First of all, it is required that all weights should be positive, and so we define a norm, the norm of coefficients. Then we define a procedure f as a sum of two functions from the ICRP database, function 8 and function 10, to represent the approximating function. Then we use this procedure with the normalized weights as an input parameter for nonlinear fitting function in order to determine those values for P1 and P2. Once we have these values, here we are, we can calculate the weights using this formula. So we calculate Q8 and Q10. Once we have those weights and using the values from the ICRP database for 10 dose coefficients, we can easily determine the approximated dose coefficient as a sum of E8 times Q8 plus E10 times Q10. And here we have our approximated value. Next, I would like to present several examples of how we can approximate continuous monotonic increasing functions with a sum of log normal distribution functions according to the just proposed method. On this slide, we have a simple bimodal distribution, and you can see that we're using an approximation of just 2 points with the same weights, 0.5, and we use F4 and F9. On this slide, we have a multimodal distribution, and we have 4 points with the same weights again, 0.25, and some F4, F6, F7, F8. So this one, this one, this one, and this one. And we have 1, 2, 3, 4, 5, 6, 7, 8 points. Moving next, we have a hyperbolic function and the following approximation with different weights. Still we're using F4, F5, F7, F9 this time, and we have our approximation calculated according to this formula. Also, we have a Residual distribution with the following approximation calculated based on F6, F7, F8, and F10. And on this slide, we have a reference to the ICRP database that we have been using for this study. So thank you very much for your attention. And if you have any questions, don't hesitate to reach out to us. Thank you.